We're very happy now to have Adam Thompson joining us to talk about coming online. And if you have questions, you can either save them for the end of the talk or you can ask them in the Slack channel.
Thank you. And thanks, everyone. It is a pleasure to be at my first in-person SciPy. I presented in 2020, and we'll get to some of this history here in a little bit. But the goal of today is to talk about sensors and instruments. I am the product lead of computational instruments at NVIDIA, and what this really means is I'm responsible for defining the hardware and the software platforms to revolutionize our instruments that we use for science to be software-defined, AI-enabled, scalable, and easy to use, particularly with handling this massive data rates that are coming from our new instruments that are producing increasingly high resolutions than ever before. I'm joined here today by my collaborator, Cruz, who's a staff engineer at the SETI Institute. And so we'll highlight some of the work that we've done in enabling real-time AI-ready scientific discovery at one of the coolest instruments that I've come across, which is the Allen Telescope Array. And the goal of this is fundamentally, the goal of that mission is to look for extraterrestrial intelligence, right? So even though NVIDIA is one of the world's largest companies, I could not find a black leather jacket emoji, but I could find a little alien. So Luigi gets that. So in terms of sensor processing, again, this talk is all about GPUs and sensors. And there is a rich history within the SciPy community, and it's something that's really near and dear to my heart. And it all started in 2019 with the release of a software library called cuSignal. So cuSignal was a library that I developed, and it was essentially taking SciPy signal, if any of you all are fans of that, and then taking that same API, but enabling that to run on a GPU. And so we released it. I made it because I thought it was helpful for me. You know, I finished grad school. I was a signal processing engineer, which means fundamentally you finish your schooling and you're an applied mathematician. And then you go to work and they're like, here's an FPGA, can you program it? And you're like, what, no? And so I was always trying to create tools that were enabling me to be more productive on the application side. So anyway, I released this thinking that like 50 people would use it. But it turned out over the life cycle of the project, we had over 400,000 Conda downloads, which was our main source of release. And I presented on cuSignal in 2020. And then through this, and weirdly through Twitter, I met Cruz, who had done a whole bunch of work with GPU-accelerated DSP. And he presented in 2022 on doing wideband FM demodulation for software-defined radios on a GPU. And he's also created a whole bunch of really amazing visualization tools which allow you in sort of domain-agnostic, like platform-agnostic tools to visualize the spectrum and explore the spectrum, right? So this is a very radio frequency story here, but we'll get into some of the general sensor processing here in a little bit. And so if we take a pause at 2022, we have tools which are well architected to focus on compute. So we as scientists and developers can say, hey, I can GPU accelerate my convolution or my correlation or my FFTs or do whatever, but we're still sort of lacking of how do I take this compute and plug it into a real-time sensor that's giving me, gigasamples per second of data or terabits per second of data to it. And so NVIDIA released a domain and sensor agnostic platform called Holoscan in early 2023, which was originally targeted to be for medical devices. So AI sidecars for endoscopies and ultrasounds and that type of thing. But we realized that if you look at a generic sensor processing platform, a lot of the core components are the same of whether you have a synchrotron or a software-defined radio or a radio telescope. And it's all about how do you get data quickly to a GPU, how do you do AI analytics there so that you can have a smart sensor, and then how do you get that data off to make decisions. And so just to finish the history here, cuSignal, with the help of our friends at Quansight, and supported by a Chan Zuckerberg Initiatives essential open source software for science grant, was formally merged into CuPy version 13. And so I want to, like, even if you're here and you're like, oh my God, I ended up in an instrument talk, this is like the power of the SciPy community, right? Is that little old me who created something kind of for me, met somebody, and then it turned into this big thing and built this community. And that's largely what we're trying to do in NVIDIA. And it's a really great story of this like private-public partnership and community-driven type of engagement. So let's talk a little bit more about sensor processing. And I'll start with some challenges. In general, and we've seen this all the time, is that the goal is to have a science programmable edge, right? We have these sensors, and the closer that you go towards collecting data and digitizing data, the more you're bottlenecked and put in a corner of having to program at the hardware layer. So this is looking at like VHDL and Verilog and programming ASICs. And kind of the goal would be, well, can I program that in Python and still be successful? And can I connect it to compute and scale it and still be successful? And traditionally, just because these instruments produce so much data that we don't know how to like interact with it in real time, we tend to store to disk, right? And so if we think about this, and I think about this, I have a 2-year-old and a 4-year-old, and I have like an abandoned toy closet, right? And I think about this when I think about storing data, because you're like, oh, this is probably important, I'll look at it later, and then you never do, right? And so like I say this as a bit of hyperbole, but Luigi, who spends his days looking for technosignatures, of looking for ET, we could say, well, we found it, but it's just sitting on some Western digital hard drive in somebody, some data center, right? And so the goal would be, can we use the power of AI and real-time analytics on this GPU platform, not only to bring in sensor data more quickly to this coalesced platform, but can we have like real-time data reduction and AI inferencing tools so that we have faster insights to our data? And then even more so, and reduce storage costs as well. And then more so, we're talking a lot about reading from the live sensor stream, but there's also a goal of how do we add AI analytics to focus on the broad scale experiment, right? To tell the scientist of, well, you entered in a parameter wrong, this is misconfigured, or to have automatic steering and tuning based off of the results of a previous experiment. So we can think in the future that maybe our sensors and our instruments look a lot like robots that can make decisions as well. Some more challenges, again, no surprise to any of you all who are familiar with this domain, but we have demanding data rates that are really hard to handle, low latency oftentimes, and we're positioning GPUs. And traditionally, GPUs are super high bandwidth, but also high latency, right? And so these workloads are looking at both high bandwidth and low latency. So we'll get into some tricks of how we handle this new world. And we also have compute-intensive algorithms, massive amounts of data, and the AI research community around non-video data, right? Like thinking of voltage measurements or radio frequency data or, like X-rays or whatever, is lagging that of just standard computer vision. So there's no like, I don't have like a model zoo to do modulation recognition or something similar. So if we look at what is our vision of the future for sensor processing, we kind of delineate this between the edge, which is close to the sensor, and then the data center and cloud, which is obviously a little bit further away from the data center, HPC center. And fundamentally, again, if you look at kind of the broad domain and sensor agnostic applications, at the edge, your first goal is just like, give me my sensor data and put it on the GPU. And then we need to do some data reduction, some data pre-processing. So think of this as like just general CUDA, accelerated computing work. And then the really great thing would be, can I take a trained AI model and apply it to my sensor stream, right? And have that be easy. And then we have post-processing, visualization, downstream reporting. And that sort of completes the edge sensor processing pipeline. And the goal here is to make this easy, right? And then at the sort of the data center side, and again, this is a vision towards the future, but it would be really amazing, particularly for these very big, expensive, esoteric instruments. It would be great to have a digital twin or some sort of simulation that is a digital representation of your real instrument that can create synthetic data used to train an AI model and then have in situ updates to your live instrument stream. So this gets into some ML ops work and scaling your sensor processing pipelines at the end. So fundamentally, what do we want and what do we need to build? And I asked Luigi's boss, Andrew Simeon, who's the Bernard Oliver Chair at the SETI Institute and is active in Breakthrough Listen as well, of what's a good sensor processing framework? Like if you're building these things, what do you want? And the answer is you want fundamentally an SDK that can deliver near peak bandwidth for UDP packets that is well documented, extensible, upgradable, AI ready, right, in case that we don't have a trained AI model to find the specific phenomenology that we're interested in. And I think most importantly, scalable to up to hundreds of thousands of sensors. The Allen Telescope Array, and we'll get into this in a little bit, has 42 separate receivers that are exploring the heavens, and that's a small radio telescope. And so the answer here is Holoscan. And so Holoscan is an AI-enabled real-time sensor processing platform. So this is what my team and I are building, particularly on the software development kit side. And it's really trying to, at the end of the day, the focus is on data management, and the focus is on developer productivity, right? If we think back to that slide that I presented of the traditional signal processing pipeline, getting high bandwidth, low latency data to a GPU is very, very painful, particularly if you want to bypass the CPU bounce buffer, have the GPU process the network stack to ingest UDP data. If you want to do a PCIe direct memory access, that involves like kernel driver modifications as well. And so the goal is that can we provide an SDK where the hard parts are done for you, and then you can tap into the sensor stream and then put in your own science, right? Put in your own work. And so that's what we've done with Holoscan. Fundamentally, you're building a directed acyclic graph up there on the left side. And these colors look a little yellow for me. It's NVIDIA green, I promise you, unless it's my angle. But these, you see that little operator graph. Again, no surprise to someone who has experience with something like GNU Radio or Simulink or LabVIEW, is you're putting boxes together, and that's your application. You can do this in either C++ or Python. And again, kind of the goal here is get data to the GPU and then allow you the flexibility and the freedom to tap in with your own work. We have multi-node and multi-GPU support available with this. We support all modern GPUs all the way down from the $300 Orin Nano all the way up to a Grace Hopper data center GPU. And we have plug-and-play inferencing backends with Onyx, TorchScript, and TensorRT optimized engines. So what this means is if you train your own model or you download a model from a model zoo, when you're ready, you can essentially just plop it into your sensor stream, and you get your AI inferencing results as well. This is Apache 2.0 license and available on GitHub. You can scan the QR code, and I have these littered throughout this presentation, so you can scan those to get more information and look at the code. If we take a closer look at the fundamentals, like the deep dive, again, remember this is predominantly structured towards fundamental platform and fundamental plumbing for you to build your real-time pipelines. And so here, Holoscan fundamentally comes with schedulers, profiling tools, and then we are a good community steward of once you have your pipeline defined on a specific GPU, data movement between each operator is done with a zero copy. So it's just you passing pointers through this. The schedulers, we have a greedy scheduler, which I like my schedulers like I like my wine, cheap and cheerful. So this is the one that comes out of the box. It's single-threaded. It just works, right? If you're just learning Holoscan or just building an application, that would be the one to choose. But we also have high-performance ones, particularly for high bandwidth and low latency packet processing, where you can pin a CPU thread to a specific operator. So when work's done, you can invoke async pipeline parallelism with it as well. And on the profiling tools, we've done a lot of work to give the flexibility to the developers to track things like latency and jitter as your data frame moves throughout your sensor processing pipeline. And then one other thing I mentioned earlier about multi-GPU and multi-node support, what we've done here is if you are leaving the warm confines of a single GPU with your data, that data movement is abstracted away with a library called UCX, which basically means that if you have access to NVLink, which is like the fastest way on a GPU server to move data, then it uses NVLink. If you have RDMA over networking, it can use that, and it's seamless to the end developer. Again, the goal is plug and play, right? Like I can hopefully plug my X-ray or plug my radio telescope into a GPU and build this pipeline and not have to worry about all of this like junk. It's not junk, it's beautiful, but you know what I mean. We're application engineers here. We also have, in addition to the SDK, we have a repository called HoloHub, which is it's where we host all of our sample applications, our tutorials, and our operators. So you see, this is a GIF that's like going through all of them. I don't expect you to like be able to see that. That's for showing the expanse of the tools we have. And again, it covers like all different types of data, all different types of like AI models, particularly for some of the medical imaging tasks as well. So we're going to take a look at each of the tools that we have and functionalities for each of the parts of building these sensor processing pipelines. So we'll start at probably the most important and the most challenging for developers, which is getting data to the GPU. And so here, we're going to make the assumption that your data is Ethernet-like, right? And we made this assumption because it allows you to scale these sensor processing pipelines in a way that is easy to use. So we have two, and again, these are all like free and open source and publicly available. We have the basic network operator and the advanced network operator. Now, the basic network operator has both Python and C++ bindings to it, and its focus is on simplicity, right? So the peak data rate that you're going to get is about 10 gigabits per second, probably more like 5. And it uses Linux sockets to send and receive data. So this works. Like you don't need a network interface card. You don't need specialty hardware. It's portable, and it's a great place to get started. So if you're building a Holoscan pipeline, one could imagine you see at the bottom left that you would take like this basic network operator receive operator, and then you would send that data to, say, an FFT that you would create as a custom operator. And I'll show you how that's built here in a second. The advanced network operator, Python bindings are in progress. So this is a C++ operator currently, but its focus is on performance. And so essentially what we're doing here is implementing GPU direct RDMA. So you have data that goes straight from your NIC to your GPU. And this is done by abstracting away the data plane development kit, so DPDK for packet processing. This is like the high rate. So we've hit up to 400 gigabits per second with a ConnectX-7 NIC and a Hopper series GPU. But again, think 100 to 200 gigabits per second per NIC and GPU pair. And one example of the basic network operator, so this is something that Luigi created, is this little video we'll play. And so on the right, you're seeing a Holoscan pipeline, which is receiving UDP data. And on the left, you see a GNU radio flow chart, which is generating IQ data, so sinusoid data. And then on the right, you'll see that we're receiving that data into GPU with Holoscan. So again, like the goal here is that with this basic network operator, you say, this is my IP address and my port, listen, and then the output of that is a tensor that you can then tap into and build your overall pipeline. In terms of the Holoscan compute operators, Essentially what we're doing here is having a framework to import your own libraries in here. So on the right side, you see the class-based definition for creating an operator. So essentially, you set your input and output ports within the setup method. And then we have the compute method, which is where you receive and send messages from upstream or downstream operators. And in here, this is all compliant on the Python side with the CUDA array interface. So I can just do cusignal.resamplePoly, and it just works, right? So this is your way to tap in. And you can edit however many input ports and output ports you want. And you can put whatever compute you want in there as well. Within the latest release, 2.2, we introduced experimental decorator support for creating these operators. So if you're more of a functional programmer, check that out. And we also, an example with the AI inferencing operator, Luigi built an AI-based FM demodulator, which is really, really cool. So typically, if you listen to car radio, you're doing this demodulation. So you're getting voice out of your signals that you're receiving via hardware. So if we do this in Holoscan without doing anything with AI, it looks like the top. But what we can do is we can train an AI model that does the resampling and the FM demod. And essentially, this reduces computation now because we don't have a resampler that we're invoking. And also the data movement is unchanged, right? So this is really amazing because you can invest in a classical pipeline that doesn't have AI in it, and then when you're ready, you can use this framework to just plop it in. And we've been doing FFTs, single precision FFTs, for decades. And so I think one of the really cool things with sensor processing is in the future, can we use these AI models to reduce our precision and actually optimize our overall processing time. The code looks like this. I'm running low on time, so I'm going to skip over this. But you can see on the right-hand side, this is the application to do that AI inferencing operator. And you can see the QR code to look at it in more depth. And then finally, we have some visualization with community tools. So again, we're trying to be good citizens with the work that we've done. And so Luigi built a Holoscan pipeline that ingested 500 megahertz of data from the Allen telescope array, did some Holoscan-based GPU beamforming and channelization, and we visualized it with his tool CyberEther. And you can see two peaks on the right-hand side. There's the one on the far right and then one close to the middle. And if you demodulate this, that's the Mars Odyssey orbiter and then the Chinese Tianwen-1, right? So we have this real pipeline that's finding real telemetry in outer space from really far away. And this introduces the work that we've done with the Allen telescope array. And fundamentally, what we've done here is we have taken their existing pipeline, which is taking in, the processing pipeline takes in up to 1 terabit per second of data. And where we used to use CPUs for packet processing, we have eliminated that with the advanced network operator and Holoscan, so that we can go straight from this UDP data produced with our front-end RF SOCs to go straight into GPU. And this reduces infrastructure cost because you don't need CPUs to do your packet processing, and we can process and handle more data in the future. So in the future, we are looking into extending this processing pipeline at the ATA, predominantly with looking at machine learning inferencing in real time to detect fast radio bursts. And then we're also investigating the relationship between building these real-time pipelines in Holoscan with GPU direct storage. So similar to the direct memory path from NIC to GPU, we're looking at a direct memory path on the consumer and producer side from GPU to NVMe. So getting started and just wrapping this up, we have this slide that has all of the places to get Holoscan. For Python, it's just a pip install. And if you're interested in learning more about Holoscan, we have a free and boot camp on September 24th, and you can register here. And finally, if you want to learn more about the SETI Institute and their mission, contact Luigi. So thank you so much for your time, and happy to answer some questions.
Any questions for Adam?
Thanks. Very, very interesting talk. I'm a little bit confused as to exactly what you mean when you say AI model here. Like, is this a machine learning classification model? Is this some kind of like large language model applied to the streaming data? What can you clarify a little bit more what you mean when you say AI?
Yeah, I'm thinking that's a good question. I'm thinking more of like a classification or detection model, right? And the goal would be that I have done some like simple convolutional neural network, like what Luigi did to do FMD-mod, and the output of that is an Onyx file or Torch script. And now I have this task of saying, okay, well, I trained this on all this offline data. I'd really like to see how it performs on a real sensor stream. And so that's what I mean by taking that trained model that you've created for a specific task and then putting it into an online sensor feed.
Hi, thanks for the talk. So when your sensor is producing some number of samples per second and your GPU is consuming a different number of samples per second, does one of those have to be strictly higher than the other for holoscan to work? Or how do you deal with potential overflows and underflows?
Yeah, that's a really great question. So we haven't investigated, and this is something that's on the roadmap, is to investigate handling like network back pressure. So we have, at least at this phase, we haven't given a ton of thought to this mismatch of like sensor versus GPU on the consumer, other than the fact that like obviously we would need for our GPU to process faster on the ring buffer that we're creating underneath the hood than the sensors feeding in. Otherwise, you have drop packets. And so one of the sort of the conclusions of this is that you would see that and you would make the appropriate modifications on the GPU side.
Just a thought. There's a Sandia extension to GNU Radio where they have some custom blocks, and one is a block buffer. And we've used it with this kind of application. And it's cool because it's like an arbitrarily sized buffer that gives you contiguous samples, and it guarantees that there's no radio overflows or underflows within the continuous block that you get. So
that's cool.
That paired with your UDP sync might be a good way to do that.
Yeah, no, I think that's a great idea, and that's exactly like one of the reasons why I wanted to be here is that this is it's NVIDIA behind it, it's like my team behind it, but it's a community-driven project, and so I'd really like to learn from you all about what would make Holoscan, and the tools that we're building on the NVIDIA side, compelling for you, and what are your hard problems that you would like to see solved here? Because this is a platform, right? Like this is the goal here is that you build your work on top of this. Like NVIDIA is not going to build like an AI software-defined radio, for example. We're going to give you the tools for you to build that.
Other questions?
Hi, I had a question about profiling. You mentioned Insight Systems and I think another tool, and I'm guessing that's more targeted towards the user.
Yeah.
I'm curious on the development side, since there's a lot of interplay between hardware at various levels, GPUs, CPUs, NVMe, networking. What sorts of tools do your team use to profile as you're developing these pieces of the pipeline?
Yeah, so there's like all of the NIC benchmarks, right, that you do that tells like how many packets you've sent and how many packets you receive. So that way you can tell if you're keeping up. A lot of that we've tried to consolidate a lot of like the standard tools that you do for like high rate signal processing into that data flow frame tracker, because like the goal there is to give you an Insight Systems type experience, but to show you like, where in the pipeline are you starting to drop packets and give you that resolution. So we do dog food, like I use the data flow tracker as I'm building applications. And then of course, as you're getting into storage, there's like specific tools for each of those that we're again trying to put that into like one meta tool as much as possible, because obviously we don't want you to be like, oh, like look at 17 different things for you to do your full pipeline.
I think that's all the time we have for questions now, but I'm sure Adam will be happy to take more questions if you see him around. So let's thank him again.
Yeah.